Good morning. We almost ended up the review part on LAN interconnection. If you remember, we said that we can have interconnection at different level of complexity and higher layer and different layer of protocols. And basically, we were focusing on some interconnections properties which refer to either bridge or switch interconnection or router interconnection or any layer above 3 interconnection types. Whereas at layer 1 we simply have basically a little bit clever amplifiers, but this is not an interconnecting device. And we've described the main properties of interconnection, which basically allows us to scale up the network performance, increasing the network capacity, exploiting the traffic locality, and all of the things we revised last week. There was just one last small part that we have to end up, which is how bridges and switches work exactly. And the point is simply that this is the behavior of the features of switches. And remember, we have to put switches and bridges in a completely transparent way with respect to the user behavior. So whereas you interconnect LANs through a router as an implication on the fact that you have to reconfigure your network, in particular network addresses, when you insert a bridge or a set of bridges or switches in your network, this has no implication. I mean, this is completely transparent with respect to user behavior. Okay? So the question is, how does this happen? Now, here we have a very simple scenario in which we have one bridge and 2 LANs. Okay? And the idea of bridge and switch operation is the following one. I want to forward on my port, so this is a bridge with 2 ports, okay, port A and port B, and the idea is that the bridge is operating only if it is needed. Okay? What does it mean? It means that, for example, in this trivial case in which we have PC1 willing to transfer data to PC2, the bridge should not do anything. So if the data are going from PC1 to PC2, since the transmission of PC1 on this coaxial shared medium already reach PC2, the bridge has to do nothing. Whereas the bridge should act if, for example, a data is sent from PC1 with PC4 as destination. In that case, the bridge should get a packet, store, read the address, and forward on the proper output port. So in the first case, the bridge will receive the packet, it will read the address, it will know somehow that PC2 is already reached by PC1 and is not forwarding this packet. Whereas in the case of PC4, instead you know that the transmission of PC1 has not reached PC4, and in that case you want to forward. That's the way in which you would like to have bridges and switches work. Because if this is not the case, which means that bridges in any case will take the packet and send on any output port, we will lose completely any advantage in terms of performance. Remember, the performance advantage is there only if you are able to exploit traffic locality. Traffic locality means that traffic which is local to this LAN 1 is not going to be forwarded in LAN 2 or in general LAN 3, LAN 4, any LAN you have in your net. Otherwise, you don't exploit any locality. Otherwise, any packet will go on any LAN, and as a consequence, the network performance will be exactly the same as if you had only a single shared medium, if any packet has to go on any segment of the LAN. Okay? So you don't gain any advantage. So we want absolutely avoid that. And this gives the first observation, that is, if in your LAN you have multicast or broadcast traffic, multicast or broadcast traffic must be carried on any link, on any LAN segment, because broadcast traffic means you have to reach any node. And the only way of reaching any node is to send this packet on any segment of the LAN. Multicast means that you have to reach a subset of nodes, but you don't know which node is interested in that traffic. So again, multicast traffic should be forwarded to any LAN to make sure that any host willing to reach it is able to get it. So for multicast or broadcast traffic, we are, oops, sorry. For multicast or broadcast traffic, we have no advantage in terms of performance because any packet should be copied and sent on any segment of your interconnected LAN. So the only case in which we can gain is for unicast traffic. Unicast traffic we gain if we really move the packets on the set of LANs in which it is needed. Okay? In this example, if the packet is going from PC1 to any PC on LAN 1, you don't have to forward on the other segment of the LAN. If instead you have traffic crossing between the two LANs, then the bridge or the switch has to forward them. Okay?
So
yes.
If we have multicast or broadcast, in any case, the bridge will operate and PC forward on port B, whatever it is.
Absolutely yes, because remember, bridge and switches should be transparent. It means that you will have the same behavior if you had a single segment. So since when you send a multicast or broadcast packet, by definition, in a single segment, everybody's getting it, you must ensure that in your switched LAN, the same behavior happens. And the only way is that every bridge, every switch forward any multicast or broadcast packet on any port. That's the idea. Of course, you don't have to retransmit. So for example, if you get a broadcast packet on port A, you don't need to send it again on port A, of course. You have only to send it on the remaining set of ports. Okay? But at the end, this packet is going to be sent on any segment of the network. Okay? In other words, we gain because we have an increasing capacity by a factor of k, being k the number of switch ports in our network, if you remember. You remember this discussion, right, we had last time. By increasing by k the number of switch ports, you will increase by k, potentially, the performance gain. But this only happens if packets are not sent on any link, because if you take a packet and you send it on all the k links, this packet is actually accounting as if it was k times this packet, because you send it independently k times. So you have a kind of increase in your input traffic, and so you don't gain anything for this reason. So let's focus on unicast only, which is the only case in which we can gain. So again, the idea is that the switch should forward only if it's needed, and needed means that only if this packet has to go to this LAN to reach the destination. Otherwise, I don't have to do that. So that implies that somehow switches should be aware of where stations are connected. Because if you don't have any idea about where the stations are connected, again, the only way to ensure that you will reach the destination is to send everywhere. Clear? If I have no idea about addresses and hosts and connection of hosts, the only way of ensuring transparency is to forward to any port again. Because in this way, for sure, I will also reach the destination. But this is something, again, that we want to avoid. So in order to avoid that, we must have switches knowing something about host addresses. Okay? Otherwise, there would be no way. So the question is, how do switches know addresses, and how do they operate once addresses are known? Well, you may say, okay, that's not so difficult. I know this topology. Okay, this is a very simple example, but you can easily extend it. I know this topology. So, for example, I can write in my forwarding table, in my routing table, whatever you want to call it, let's call it forwarding table of the bridge, that any packet whose destination is PC1 should be sent on port A. Any packet whose destination is PC2 should be sent on port A. Any packet whose destination is PC3, you should send it on port B. And any packet whose destination is PC4, you should send on port B. Right? And if you do that, you fill up this table, everything is going to work perfectly. Because if you get a packet from PC1 here, whose destination is PC2, you will read in your table that PC2 should be reached through port A, and you don't need to do anything because you already get this packet on port A. If instead you receive a packet whose destination is PC3 from PC1, you will read the destination. The destination says forward on port B. You got it from port A, and you are going to forward it. Okay? So if you put this table, no problem. everything is going to work. Now, this approach doesn't work very well, doesn't scale. Why? Well, first of all, whenever you add one station, you have to go to all of your switches. Now, in this example, which is very trivial, we have only one. In general, you have several of them, and you have to update the forwarding table, because otherwise those bridges will not be able to reach this destination. And again, if you get a packet and you don't find this address, the only thing that you can do is to send on all the output ports to ensure that you will reach it if you don't know. Okay? But again, if you do that, you lose any advantage. So whenever you add a new PC, you should go on any of the forwarding table of your switch and you add this entry. Okay? If one of the PC goes away, well, you could do that, you don't have. I mean, if you don't do that, you will have useless entries, but the network is still working, so you have to do that only if you want to make the table a little bit more compact. But more than that, any change in your topology, and any change means you are adding a new LAN, you are creating a new port, you are activating a new port on the switch, or one of the interfaces of the switches goes down, because it breaks. In any of those situations, you should go there and modify your forwarding table. Okay? So you could do that, but it's absolutely not practical. So we need to have an automated way of doing that. And normally what you do, since we have a mesh topology here, is that we exchange information among nodes about the topology, and according to that you compute the path, and you write the best path in the nodes. That's normally what you do. And that's what, for example, routers do. Okay? They exchange information about the topology. On the basis of that, they compute the path, and they write in the routing table this information to make sure that the forwarding happens in the proper way. We want to avoid to do that here in switches, okay? Because we want to have something which is simpler. So what's the basic idea? And we want to have something which is automatically updating. So the basic idea is that every switch is operating through three features. The first feature, which is called address learning, so we will learn addresses. So at the beginning, when you switch on a switch or a bridge, there will be no forwarding table. The forwarding table is empty, which means that any packet is sent on any output port at the beginning. Okay? Whereas, while you start seeing packets in your network, you will start learning addresses. Okay? Once you've done that, which is the way in which you populate your forwarding table, then you have to make a decision on how to forward packets, depending on what you find in your table. And finally, as we will see in a moment, you run a protocol, an algorithm actually, which is called spanning tree, to ensure that on any interconnection topology that you may create, you will build a logical tree, and you will forward packets only on that logical tree. And why is that? Because the learning algorithm that you use is very simple, but is working properly only on a topology which is loop-free. And the tree is one of these topology which is completely loop-free. So these are the three main functions. So the basic idea is the following one. The address learning phase is based on the so-called backward learning algorithm. So imagine that the switch is a device which is at a given cross point. So you are in a square, and you have several roads coming in this square and going out of this square, right? Any road is typically bidirectional, okay? So the switch is the square. And when a packet reaches the switch, it has no guideline about the network topology. You have no idea on how to move. So you are driving a car, you know that you want to go there, you know the destination address, but you don't have a map. You have no idea about the topology, and you reach a square. And you want to go to a given destination. And what you're looking for is a sign that tells you, okay, if you want to go to Milan, you have to take this road. And if you want to go to Naples, you have to take this other road, and so on and so forth. Okay? If you don't find it, which means that the table is empty, you are cloning the car, and you're sending a copy of the car on any road, right? And so, as a consequence, you will also select the road which gives you to the proper destination. That's the basic idea. Is it clear up to now? So as I said, when you switch on your road system, you reach a square and there is nothing written in that square. There is no destination node, okay? But you are the square. You are the switch, you have some intelligence, and you read that there is a car coming from a given road, and this car is willing to go to a given destination. But you also know the source address. You also know that this car is coming from Torino, for example. So you are in a square, you get a car in the square, and in this car there is written, I'm coming from Torino, I want to go to Milan. Okay? Now, if Milan is known, you will forward. If it's not, you will clone on any output port. But reading the source address, you will know something. Since this car has reached you from this road, you know that by sending packet on that road with this destination as Torino, you will reach Torino. So you know by learning the source address that you can write in your table that the destination, Torino, can be reached through this road. Is it clear? So I have this road coming here, there is a car in which is written, I'm coming from Torino, I can write in my table, okay, this road reaches Torino. Is it clear? So I will put in my forwarding table this information that I will use later for other packets that has to go to Torino as a destination by looking at the source address. That's called backward learning. I will learn the path on the basis of the back path with respect to the packet coming in. Okay? Now this works perfectly well only if you have no loops in your topology. If you have loops, then you can demonstrate that this algorithm is not only not working properly, but it may create a situation in which you have packets which travel forever in your LAN, or you will have destination that will not be able to reach because the signs that you have in these squares are not coherent. And so you enter a loop, and remember, the only way of reaching the destination is to drive, look at the sign and go there, look at the sign and go there. If for any reason you create a loop, you will never reach the destination. And both of those things can happen if you have a topology which have loops. So the backward learning is not working properly on a mesh topology. You have to create a tree. That's why we need to run the spanning tree algorithm. Is it clear? Any question about that? So, in summary, so these are switches. Okay? So we may have LANs here. So we may have, for example, this is a LAN, this is a LAN, this is a LAN, if the technology is a coaxial cable, okay? And on those LANs, we have users connected, okay? So these circles are bridge or switches, clear? And what we have to do is that, you see here, this is not a tree, this is a mesh. So we have to create a tree on this mesh. How? Basically by pruning some of those connections, by deactivating some of those ports. So for example, according to a specific algorithm, if we don't want to go into the details, doesn't matter, there are automatic rules so that when you switch up your switches, they will start exchanging some information and they will build this tree. For example, suppose that the tree, which is again a logical topology, oops, it may be something like that, okay? I think this is a tree, if I'm not wrong, and if I'm not wrong, this tree connects all of the switches, okay? So you see that there are several links, and if you want, several ports which are not actually active. You see, this port is inactive, this port is inactive, this port is inactive, and so on and so forth, okay? All of the green ports here are not activated. It means the bridge are not reading packets and are not forwarding packets on them. So the only portion of the network in which you will see packets is the red one. Okay? And that's a limitation, because we are subtracting from our network a lot of capacity, because all of those links will never be used, right? So we have the potential of a given capacity, and by pruning it out, we reduce the network capacity. We are only operating on a subset of links. Why? Because we want to use a very simple and trivial algorithm, which is the backward learning I described before. Okay? Now, as you know, in a tree, there is only one path to reach any destination. And as a consequence, there will be only one path followed by that source to move in the network. So that's why the backward learning is working properly. Okay? I'm sure that if you reach this point from this path, by following that path, I will reach the destination. Okay? Note that the nodes have no idea about the length of the path, the number and how many and which switches you are going through to reach the destination. You have no idea. You just only know that by going in this direction, I will reach the destination. That's the only information I have. I have no idea about the path length, any information like that. Just reachability. So there is no node that, for forwarding purposes, knows exactly this topology. Okay? Is it clear? Now the details about how the algorithm works are not so important. Okay, there is a known algorithm, it is working. And this algorithm runs in polynomial time. If you remember, we only discussed about multicast in a mesh topology. I told you that building the optimal multicast tree is NP-hard. The optimal multicast trees, which is reaching a subset of destination, is, and making it optimal. Optimal means of the shortest path. It's NP-hard. It's called Steiner tree problem, is the NP-hard. There is no polynomial algorithm node that allows you to reach it. Whereas the spanning tree, which means reaching every node in your network, it is polynomial. The complexity is polynomial. Okay? Is it clear up to now? So again, remember, we are moving from a full shared topology, single link, shared by everybody, which is fair, which has a lot of good properties, but has also limitation in terms of capacity. We are moving to a mesh topology, okay, which makes the network, if it's fully switched, just equivalent to a point-to-point technology, so we are losing the concept of shared medium. Any medium is dedicated, okay? And furthermore, on this mesh topology, we are only going to use a subset of links in order to make sure that everything works as if we had only a tree topology interconnecting switches. Is it clear? Any question? Yes. It is being standardized within the framework of IEEE 8.2 family of protocol, if you remember. So that protocol is standardized, and if you're selling an Ethernet switch, you are supposed to implement and run it. Okay? And it's a deterministic algorithm. Once you have assigned addresses and weights to the port in a given network, any time that you run it, you will obtain the same tree. Okay, so it's a deterministic approach. If you want to change the tree, you have to change either the addresses of the switches or the weights of the ports. Okay? Now you may wonder, is there any other question? Yes?
For meeting the address learning, can I send the packet to myself or another user of my LAN so that
To fill up, you mean to
fill up yes, the table in the first piece.
So the question is, to fill up the table, I can send a packet to myself, basically. Yeah. Okay. Yeah, that can be done, of course. It doesn't make a lot of sense. Take into account that the hosts are not aware of the fact that there are switches. You don't know. So if there is no switch, there will be no point in doing that, right? So you have to remember that users, hosts, operate as if they were operating on a real shared medium LAN. So they will not change their behavior. Now, of course, in principle, you could do that, but I mean, it's not really needed. The only drawback that you have is that at the beginning, for the first packet that reaches a given destination, you will lose some capacity because you are forwarding on any portion of this tree. That's what you are really losing.
Maybe when I have to use for the first time the network, all the users could do that, so that the killer will be
Yeah, again, what advantage do you have? This packet should travel through all the network, right, in any case, which is what's going to happen for the first packet that you generate to reach a given destination. So you have exactly the same load, and you don't gain absolutely nothing. So you generate additional traffic for doing something which you will do in any case when somebody is trying to reach you. So it's really complete, or when you generate the first packet, to be more precise. So it's absolutely useless. Okay. Now, the question that you may ask to me is why we are not building this topology as a tree, as a physical tree, which would avoid doing that. And the reason is that for redundancy, simply for redundancy. Whenever you create this type of network, you want to be redundant against faults. So what's happening if there is a fault? Well, if there is a fault of one of the links that you are not going to use, nobody will detect it. But if there is a fault on one of the red links, then the nodes will detect it, and they will reconfigure the tree in such a way that you still have connection available for any type of nodes. Okay? So that's why you typically cable physically your network in a mesh way. You know that you are going to use a subset of links, but the other one, and a subset of ports as well, but the remaining links and ports are there, and you will use them in case of faults for recovery purposes. Okay, so it still makes sense to cable in this way. Okay, so if, for example, in our case, this cable will break, you have to rebuild your tree, and you will, for example, end up doing something like this. The new tree may be something like that. So you may even completely change the tree. It depends on which links breaks. It depends on how the algorithm is going to work. Okay? And this is typically done in an automatic fashion. It's not as fast as the 50 millisecond reconfiguration of the single link. It's a little bit more complex because you need to exchange a lot of information among bridges. You have to resolve and to make to build this tree, identifying which is the root of the tree. And so the process is fairly slow. It's more complex than detecting a single failure on a link, of course. But at the end, you will converge to a new topology. Okay?
But this enters with a specific, is part of this algorithm, this control.
Okay, this algorithm is running periodically, basically. So you keep exchanging information, which is basically addressing information among nodes, and as long as you don't have any new information, you will keep the old tree. If the new tree comes in, you will get different information because, for example, this node will not exchange the ID anymore, and you will automatically rebuild the tree. Okay? It's fully distributed, and is which is running it. And of course, as a consequence, these entries in the forwarding table may change. Okay? And so in order to make it simpler to manage it, these entries will have a soft state approach. Soft state approach means that when you detect a destination, you will write it, and after a given timeout, you will cancel this information so that you will get adaptive to the new situation. If there is a new situation, for example, this node here that was reached from this link, from this node, so suppose that you have a destination here, a blue destination here, okay? That's the user. So in the previous case, when we had the red topology active, this node here had to send on this output port to reach this destination, the blue destination. Remember that we are always reaching users, not switches. So to reach the blue user on this node here, we have to write send on this output port, correct? Whereas when you reconfigure everything on this same node to reach this blue link to the blue user, you will have to forward on this path here, so on this port. Okay, so you have to adapt your forwarding table and match it in the new case. And this is done in an automatic way. Okay? So from our perspective, we have to know that besides of the detail, we have to know that we have two choices. Actually, we have three possibilities. One is a full shared LAN, the original one. We have a single shared medium. All of the nodes are connected to that one. We may have several segments of cables interconnected by repeaters. It doesn't matter. It's still logically a single cable. Everything is working as if it was a passive bus or a passive star, a single channel, capacity C, n users. At most, we can get C divided by n per user if all of the users are active. The other extreme is a fully switched network. In a fully switched network, every user has a potential of getting C capacity, okay, depending on traffic locality, depending on traffic distribution. Okay? In that case, you have absolutely no collision, so we don't have a LAN anymore. We don't have any sharing at all. It's always and only devoted capacity, dedicated capacity, okay, on any point-to-point link. And then we can have everything in between, okay? We can have hybrid situation in which you have partly switched and partly hubbed, partly bridge and partly full. It depends, and that will be a mixture of multiple access and multiplexing. And the performance will depend on that. As soon as you start to have a switched topology, remember that the switches are acting in such a way that you are building a logical tree. So you are operating on a subset of those links. So your link, your topology capacity will be the summation of the links in your tree. You may have additional links, you can't use their capacity because these are set up apart for fault protection reason. Okay? This is the summary of lessons learned here. So this is how actually the address learning phase works, okay, fairly easy. And also how frame forwarding works. So you get a packet with a multicast destination. You may find it in the table. If you found and is coming from the same port from which you have got it, you drop it. If you found the address but the port that you have to forward on is different from the one from which you have to got it, you will forward on that port. So if you have to send it on port Y and you got it on port X, you will forward on port Y. If you don't found it, you will forward on any output port, any active output port. Remember, some of those ports may be inactive, okay? And if the packet has a multicast or broadcast address, you will always forward on any output port except the port from which you got it. Okay? So multicast, broadcast, and unknown unicast will have the same behavior. You get it from one port, you will forward on any other output port. Okay? That's it. Here there are some details in which, on a very simple case that is written, why, if you have a loop, you see here we have a loop among bridges. Okay? In this case, if you are running the spanning tree algorithm, you will get problems, and the problems are explained in the next slide. It's not so important from our perspective, it's just for completeness. If you are curious, you can read it and try to understand better. It's not so fundamental. This is a summary of bridge, switch, and router properties. This is what we have described last time. And that's basically it. Any question? Okay, just one additional thing that may have interest from our perspective is the concept of virtual LAN. So the virtual LAN is a technique or a technology, if you prefer, that allows us to further partition nodes and switches as if they were operating on separate LANs, logical LANs, even if they are sharing the same physical or logical topology. So basically the idea is that you extend the PCI, the protocol control information, the header of the MAC packet. If you remember, we have seen last week the header of the MAC packet. What do we have in the header of the MAC packet? So that's a kind of review. Any of you remember what are the fields that we have in the Ethernet packet? Source and destination address, which are very long, is 6 bytes, yes. There was a preamble, there was a set of headers that allows us to recover the synchronization because it's an asynchronous transmission technology, right? The CRC to detect errors and to drop wrong packets. And then there was the protocol type or the packet length. And that is it. Then we know that to separate packets, we have to wait. This is not actually a packet header, it's just a silence on the channel. Okay. You have to add to this packet header one additional field, which is the VLAN ID, the ID of the virtual LAN. Okay? And basically, the idea is that if you want to use the technology, you can assign a different VLAN ID to subset of hosts. So let me take this example here. So in this example, we have, and you see these are two equivalent examples. So we have here 4 coaxial cables and 2 bridges interconnecting these 4 segments of LAN, okay? If you look at that, this is already a physical tree. You see that? There is no loop among bridges. This is not the way in which you would cable a real network, okay? On the right-hand side, we have exactly the same topology, the same behavior. The only difference is that these devices are called switches because they are not running on coaxial cable, they are running on twisted pair. And you have direct connection with the host, okay? So this is actually no, this is not correct. It's not true. Why is it not true what I said? Why these two topologies are not equivalent? I said something wrong. These two topologies are not equivalent in terms of performance. Besides of the fact that on the left-hand side you have coaxial cables, on the right-hand side you have twisted pair, okay, but why they are not equivalent? Number of ports, yes, yes. If you look at the bridge and at the switch, the bridge has 3 ports actually, and the switch is instead has much more than that. Why? Because on the left-hand side we still have some sharing, okay, here. These 4 nodes are sharing this channel here. So in order to make this topology equivalent, we should have a hub here interconnected to the switch, and these 4 nodes interconnected to the hub. In that case, it will be equivalent, because we will have some sharing of resources. In this case, you see, this is a fully switched solution. Every node has a direct link to the switch. So that's fully switched. There is no sharing of resources. There is no collision, no contention. So we have a much larger capacity on the right-hand side. Okay? In terms of, instead, possibility of partitioning nodes, they are similar. And you see here that we are partitioning our LAN in 2 logical VLANs by assigning to the gray nodes a given ID. Suppose this ID represents the color, okay? And to the white node, another VLAN ID. And we can do that both on the left-hand side and on the right-hand side. So whenever one of those hosts is going to generate a packet, it will add to that packet a VLAN ID in the packet header, which will be gray if you have been assigned to the gray VLAN, or it will be white if you have been assigned to the white VLAN. Okay? So that's how you will distinguish among the packets generated on the same physical infrastructure. You see the physical infrastructure is shared, but you have 2 logical LANs. Okay? And the direct communication is only possible if you belong to the same VLAN. Otherwise, you have to interconnect the 2 VLANs through a proper device to move from one VLAN to the other one. So that enables to have several logical separated networks Okay? When you generate a broadcast packet on the gray VLAN, this is not going to be forwarded to the white one. So that limits the broadcast forwarding, for example. Okay? That's one of the advantages of VLANs. Okay? You are, again, logically partitioning your network. Now, that may have an implication on performance. Which implication? Well, we have to study with care. It depends. Okay? It depends on where the two networks are interconnected. It depends on many, many things. The first main difference is that when you generate a broadcast packet, if you were not using a VLAN, this broadcast packet will go on any link. Whereas, if you separate it in two VLANs and you generate a broadcast on the gray, the broadcast is going to be only on the gray portion of your network. Okay? Which is the impact in terms of performance? It depends. If you look at this case here, you see that we have gray nodes here, here, and here, only on 3 over 4 segments. So when we have generating a broadcast packet on the gray network, we save one transmission, because on this LAN, there is no need in sending it. Is it clear? And the same holds for the white LAN. You see the white LAN only is going to cover 3 LANs, 1, 4, and 2. You are not going to forward a broadcast white packet here. Okay? If instead you have distributed these gray and white so that at least one of both will be present in any LANs, any broadcast packet will be forwarded on any segment of LAN by definition. So you will not gain anything in this case. Okay? Of course, the gain is much more significant in terms of saving for broadcast when you have a fully switched network. Because when you have a fully switched network, broadcast packets will only go on the links where it is needed. So gray packets will go only on gray links, white packets will go only on the white one. So in that case, you will gain a lot. Okay? So this is how the interplay between broadcast unicast packets, partitioning among VLANs or not, and positioning of the nodes with respect to traffic distribution. So try to, again, think about it a little bit, because this will have a significant impact in terms of network performance, etc., etc. Any question? Of course, you may have a portion of your segments which are VLAN aware, able to deal with this extension, and some other portion which are not for compatibility reasons. Remember, always we are always trying, when we extend something, to keep it compatible with the previous existing standard. So whenever, for example, Ethernet has been designing a new transmission speed to increase the network capacity, okay, we have 10 megabit in the Ethernet, we have 100 megabit, we have 1 gigabit, we have 10 gigabit, and so on and so forth. Whenever you introduce a new bit rate, a new physical standard, the card should be able to downgrade it in case you connect the card to a switch which has not this capacity. Always trying to keep compatibility. So VLAN support is good, but if you are not able to deal with that because your card is not able to support it, the network still should be able to operate. Okay? So in this example, you have what is called a legacy domain here, which is unaware of VLANs, unable to tag packets, and here you have a VLAN aware area, and whenever you move packets from here, which host generate without the VLAN ID, because you are not aware of VLANs, you will have a device that will tag, will add this VLAN ID at the place of the host to move to the VLAN enabled or VLAN aware portion of the network. So maybe this tag is not added by card in the host, it may be added within your network in some switches, depending on how your network is organized. Okay? Is it clear? This is to allow the coexistence between VLAN aware and VLAN unaware host or device. Any question? And this is where the VLAN ID is going to be. So you will exploit this length field with a reserved code which tells that, okay, the packet has been extended according to the VLAN standard. So there is one reserved code here, which is devoted to identifying the packet as being VLAN aware. If this code is used, you know that there are 2 additional fields here in this packet format, okay? If instead you have another number here, that's a standard legacy E802.3 Ethernet packet, okay? So that's why how you can keep compatibility. In the tag, there is this VLAN ID, and there is also this priority field that we will revise later to understand which are the features in terms of quality that are provided in this type of network. Okay? That's a layer 2 protocol comparison here. So we have the protocols we have revised here. How do they do the packet delimitation? How do they implement the packet delimitation feature? How do they implement the protocol, layer 3 protocol multiplexing? It means carving information about which layer 3 is using this layer 2 in order to give it to the protocol layer, the proper protocol layer at the receiving end. Okay? You have IP here, you will always find in these fields IP. But you may have other routing protocol that you may run. Okay? Today it's not so popular. 10 or 15 years ago it was more popular. So this is how do you do layer 3 protocol multiplexing. Whether you have error detection or not, whether you have error correction or not, you see yes in lap B, optional in lap F, no error control in ATM plus AAL, no error control in Ethernet, and which type of QoS support that we will discuss a little bit later. So QoS support means, first of all, being able to distinguish what a user flow is. When you have a virtual circuit, you exactly know what a user flow is. Whereas in Ethernet, this is not available because there's a packet switching with datagram techniques. We will see that one way of supporting QoS, it will be through the exploitation of priority bits. Okay? Any question? Okay, good. So that ends up layer 2. We have just few things to revise about the Intel protocol, then we can start with the new concept. So in the Internet protocol architecture, first of all, this is the set of pictures that you may see that describe the Internet protocol suite in terms of protocol architectures. You see that it's not so different from the standardized 7-layer model of OSI, and in particular, what you have seen up to now for the layer 1 and 2, or physical and data link, holds also for IP, because IP is able to run, by definition, any technology. So give me any technology that is able to send bits from here to there, okay? Or if you prefer, is able to send IP packets from here to there, fine. For me, it's okay. It can be friend relay, it can be X25, it can be ISDN, it can be ATM plus AAL, it can be Ethernet, I don't care. It can be anything else. The Internet Protocol Suite starts describing protocols moving from layer 2 and above. So layer 3, layer 4, application layer, and potentially several other sub-layers in some scenarios. So what we are interested in is mainly to review very quickly a little bit information about these two layers, which are network layer and transport layer. Remember, the transport layer is running only in the host, not in the network, only end-to-end. In the network, you will have layer 1, layer 2, and layer 3, which is IP, plus some additional protocols that are mainly there for routing purposes or addressing features. So what is the IP protocol doing is basically doing very little, if not moving packets from a given source to a given destination. So here we have a packet format definition at layer 3, We have the address format definition, which is fairly important from some perspective, and then we have the data or forwarding procedures that have been defined. The IP protocol does not provide any type of support for quality of service. We have seen some support of quality of service, if you remember something. Like we have seen some bits in frame relay to allow the user to generate a little bit more than the negotiated rate. We've seen some bit for congestion notification or in frame relay, and the same in AGM. We have seen that you have priorities in Internet. In the Internet, basically, we have no support at all. Okay? So it's the so-called unreliable service. There is no guarantee that the packet will be delivered. If you are able to do that, you will do that. But if you, for some reason, you are not able to do that, you fill up a buffer which is filled up, you will drop the packet. And that means that the service that you provide is not reliable. There is no reliability guarantee. Okay? And there is no QoS, and it's fully connectionless. So there is no virtual circuit. You just wake up, you take the packet, you generate, you put a source IP address and destination IP address, which are unique worldwide, and you send, and that's it. Pure datagram service in a packet switching network. Okay? Why? Well, there are some reasons. One main reason is that you want to keep the node simple. And the simplicity from this perspective is related to the fact that you have no notion of connection in the network. So you may have a user generating tons of packets for the same destination. All of them are treated independently in each node. So you don't need any forwarding table. You only look at the routing table. You go there, you look for the route, and you send. Next packet comes in, you make another routing decision. So if you generate tons of packets from A to B, in principle, any packet can follow a different path. Depends on the routing policy you adopt, which is not true for virtual circuit. You know that we have ordered guaranteed because we are following always the same path. Okay? In this case, it's not true, at least in principle. In practice, what's happening today in the internet is that unless very strange situation, which may be link failures or parallel links among routers. So you have a space diversity among two routers. You have several cables connecting to routers. In that case, you may detect some out-of-order delivery. Okay? Otherwise, normally, that's not going to happen. Why? Because we are following a single route per destination. So the routing algorithms and protocols used in the internet today write in the routing tables of the routers only one path per destination. So as long as you don't change this information, every packet it will reach this node, it will say, okay, go there, go there, go there, and you will keep going in the same case, unless there are failures. If there are failures, you recompute the path, and of course the situation changes. Okay? This approach is called stateless, in the sense that you don't have any knowledge about active connections, you don't have a forwarding table, and everything is soft state. You don't have to keep information about which are the active user connection crossing a node. Whereas in circuit switching, we do that, remember, for every circuit we had one line, and in virtual circuit as well. For every virtual circuit crossing a node, we have one line, one entry in the forwarding table. Okay? Why we may drop packets? Well, for failures, a router goes off, a link goes off. Okay? There is a mistake here. Okay. So in case of failure, you drop the datagram and you send a message to the source saying, I dropped this packet. If you have a buffer shortage, which means that the buffer is filled up, you drop the packet and you can do anything because you cannot write the datagram, so you are not able to read the source address, and so you cannot send a message to the source telling, okay, I had a problem, of course. So if the buffer is filled up, you drop and that's it. If there is a checksum error, so there is an error control, but only over the header, so basically there is no error detection at the IP layer on the data. There is no error detection at the IP layer on the data. There is an error detection on the checksum, on the header, to make sure that the address is not wrong. Okay? If there is a checksum error on the header, you drop the datagram, and of course you are not going to send anything because the address may be wrong. So there is no point in sending to a wrong source. Okay? So you are dropping for header checksum error, for buffer shortage, in which case you do nothing, or if there is any failure, in that case you drop and you send a message back to the source. Okay? That's it. That's the packet header. There is not much to say, actually. Let me go through it, and in the next slides you will find the description of all the fields. So we have two addresses here, the source and the destination. You see that this packet format is of multiple of 32 bits. So every line here is 4 bytes. Okay? Every line is 4 bytes. If you compare this packet header with ATM header, which was 5 bytes, this is 4 times larger header. It's 20 bytes. And part of the reason is because of the addresses. 8 bytes of this header are for addresses. Why? Because these addresses should be unique worldwide, so we need a lot of bits. Okay? Source and destination IP address. What else we have? Well, we have a version field, which is today 4. There are some portions of the network which are exploiting IPv6 format indeed, not so many. Keep into account that IPv6 has been designed in the early 90s with the goal of substituting IPv4 in few months because we had a shortage of IP addresses. So that was 1992 or something like that. Okay? And we basically survived with IPv4 up to today. So here it's written 4. If it is written 4, that's the packet header. Okay? Then we have the header length, which is typically 5 bytes. Sorry, 5 lines of 4 bytes each. Why we need it? Because we may have options. If we have options used, we have a longer header. Okay? So we will change the header length field. Then we have the service type, which has been designed starting from the beginning to support priorities, but which has never been used until, again, the 90s. So for about 20 years, it has been completely disregarded. So basically, even if the service type field is there to set priority on the packets, routers, normal basic routers with no extension for QS support are not using it. Okay? Then we have the packet length, which is since the variable packet size up to 64K, that's the maximum packet size, we write here how large is the packet. Now here we have one line which is used for dealing with fragmentation. I will come back to that in a moment. Then we have the time to leave, which is one field which is used to avoid having packets looping in your network forever. This field works in the following way. You get a packet with a given time to leave, you decrement it by 1 when you send it out. Every router you cross, you make it -1. Okay? So suppose that the time to leave initially was 16, it means that you can cross at most 16 routers. If you cross more than that, the router which will receive the packet with time to leave equal to 1, it will decrement it, it will go to 0, it will drop the packet, and will send a message back to the source. So if you, for any reason, routing error, routing error, you have a loop, after a given number of hops, this packet is going to be dropped by the network. Okay? Then we have the header checksum here. Which is error detection capability on the header only. Okay? And then we have the protocol field, which again is protocol multiplexing. So we can write here, which is the transport layer protocol, which is using the IP packet. It can be TCP or UDP today. Okay? It's protocol multiplexing. Which upper layer protocol I'm covering in the data portion of this packet. Remember that the upper layer protocol is going in the data portion here of layer 3. Okay? Any question? Now, oops. Now this line here, and I don't want to go into the detail, they are written in the slide, it's not so important, is the field used to deal with fragmentation. What is fragmentation? That instead is important. We have already said that in some case. Fragmentation is the process of taking a packet and given to the fact that we are not able to carry a packet of this size on that technology, we have to chop it. We have seen that, we name it segmentation, if you remember that, in ATM. AAL is getting a large packet from the above, and you have to carry it in 48 bytes. So you segment it, you chop it, you put in cells, and then you rebuild it at the receiving end. Okay? Now, IP may need to do that. Why? Because you have IP routers here. These are IP routers. Okay? And on these links here, you have no idea about which technology you are going to use, right? You don't know. You want to be able to run on any layer 2. And as you know already, different layers 2 have different bounds on the packet size. Okay, we have seen that, for example, we have for frame relay, if you remember, 4096 bytes. For AAL, we had, I don't remember, which is the packet size. Do you remember it? It's 9,000 bytes, something like that. It was written in some slide. I don't remember. It doesn't matter. It may be 9,000, something like that, but I'm not sure. We have to check. But in the slide it's written. For Ethernet, is 1,500 bytes. Okay? So we have different sizes. And suppose that you get a packet here from a given user with a given size, and you have to send it out here, and for some reason, the maximum packet size on this link is smaller than the packet size. What you have to do, you fragment it. You have to chop it. And this is done by IP. So the IP protocol is taking one IP packet, is chopping it, in our example, in, suppose, 4 portions, and you will actually derive from it 4 IP packets. So every fragment is again an IP packet. So you have the same size in terms of error here. Okay? That's fragmentation. Simply because this packet size here was not permitted on this link. Okay? Now, the details on how do you do the fragmentation process are not so important. You basically need to have some fields to make sure that you put the fragments in the proper ordering, okay, at the receiving end, because then you want to rebuild this at the receiver. You need to rebuild this IP packet that has been generated here at the receiving end, getting those 4 segments out. So clearly, again, fragmentation is bad because we have more overhead, and here every overhead is 20 bytes. So if you create 4 fragments from a single IP packet, you will have, instead of only 20 bytes of header, 80 bytes of header, 20 bytes for each of the 4 fragments. Okay? And then again, if you lose one of those fragments at the receiving end, you will not be able to rebuild the original packet, and everything must be dropped, as we have said many, many times. Fragmentation is something that if you can avoid, it's better that you avoid, because you have more overhead, higher loss probability, etc., etc., useless traffic, and all of the things we have seen and discussed when we talked about ATM. We again see the same problem here. Yes? No. The IP protocol states that once you have created an IP fragment, the process of rebuilding the original IP packet is run only at the destination, to avoid doing that within the network. So routers may need to segment packets, to fragment packets, because you don't know. Typically you do that, actually you typically do that in routers, because at the source you will create from the beginning packets that will fit your packet size. There is no reason to do something different from that. So if your link is an internet link, you will start creating packets of 1,500 bytes. Okay? And so you don't need to segment or fragment at the source. In the process of going through the network, you may need to do that, and if you do that, you will rebuild at the receiving host. Unless we are talking about a packet that has to be sent to a router for management purposes, for example. If the destination is the router, of course, the router in that case will rebuild it, but only in that case. So you will rebuild at the destination, not in the network, to keep the network simple. Instead, the fragmentation process is started typically in the network when it is needed, when you have to do that. Okay? And this is the reason why you must run IP on top of AAL. I think we said that, if you remember, we said that if you run IP on top of frame relay, you may have the LAPF control, but this typically is not used. Remember, the LAPF control is creating an error recovery mechanism with retransmission and window protocol, and you typically put it on top of the LAPF core part. Okay? This is the typical architecture of IP on top of frame relay. Whereas if you have IP on top of ATM, you cannot put ATM directly below IP. You must have AAL. Why is that? Because if you had this scenario here, IP must generate IP packets of 48 bytes, right? So you have to fragment, and the fragment size will be 48 bytes, correct? And in these 48 bytes, you should put an IP packet whose header is 20 bytes. So in every cell, you will have 20 bytes of header, of IP header, and the remaining part of data. So that will be absolutely not possible. And IP should fragment any packet. So it will put a lot of load on the routers, and it would make the utilization of the link absolutely not acceptable. So you are forced to put IP on top of AAL. Then AAL can accept large IP packet, and then it will be a task of AAL to segment, but we know that AAL5 is very efficient in doing that. You will not lose, you will not have any overhead. Okay? So if you go back many, many slides, let's do that in this way here. Here If you go back to this slide, which was describing AAL5, this payload here is 64K. It's much larger than I remember. Okay, the maximum packet size is 64K. Probably 9,000 was the packet size of AAL3. I don't remember exactly. No, maybe not. It's not written here. Doesn't matter. So that's the IP packet. So you will come out with a packet of any size, basically, because the limitation is very, very large here. So that will be the IP packet with 20 bytes of IP header and the data. Then you will add these fields here, and then AAL will carry on ATM. So IP does not need to fragment at all. You take the packet as it is, you pass it to AAL. AAL is segmenting it for you, carrying on the ATM link, rebuilding this packet here at the AAL level, and then you will extract the IP packet from the AAL packet, and you pass it to IP. Okay? Clear? And that's why you must have IP on top of AAL. IP directly on ATM is basically not possible. Otherwise, IP should create IP packets of 48 bytes, which is clearly not reasonable, having 20 bytes of header on any packet. Okay? So that's basically it. In the next set of slides, you have some description of these fields. Okay? You can go through it. There are some details about the fragmentation. In particular, it's written that the fragments are reassembled only at the destination here. This is the question that you asked me before. Okay. And the summary of why fragmentation is not a good thing. I didn't mention that, but there is a mistake here. Sorry, it's reassembly here. It's full of typos, this slide, sorry. I didn't mention it. The other issue with fragmentation is that not only you have this useless traffic, and if you lose one segment or one fragment, everything is lost, but also you need to have timers at the receiver, because you cannot wait for a fragment forever, right? So you have to put a timer, and after a while you have to try to put the fragments together and see if everything is working or not. So there is also this additional complexity, which is typical of any reassembly process. You start reassembling, and then if you don't get a fragment, you have to make a decision. After a while you have to drop everything, right? And that's basically it. And the last sentence here tells you that IP over ATM needs AAL to avoid IP fragmentation on ATM cells. Another mistake here. Oh, boy. Okay? Details on how it is done. Time to leave, I told you what it is. The protocol, higher layer protocol code is TCP UDP plus some other cases for non-user traffic, for monitoring and control. Header checksum, source and destination address. Now, the most important thing, there are many details about addresses. We have to skip, we don't have time. I want you to remember a few things. First thing is written here. The IP address is actually composed by two parts. One which identifies the network to which the host is connected to, and the other one which identifies the host within that network. And the routing process is only dealing with network reachability. So routers only look for destination networks. Only when you reach the destination network, you'll use the host ID for routing purposes, for reaching the destination. Okay? So that will clearly simplify and reduce the number of entries in the routing table. That's the main issue with routing table. In principle, routing tables should contain one entry per destination, and that doesn't scale. In the example we were discussing a couple of quarter of hours ago, it means that when you are driving without a map and you reach a square, you should find one sign for every destination in the world, which is not clearly possible. It's not scaling. To avoid that, there are several techniques. One of them is that instead of having a single address of every destination user, which is the IP address, okay, you will start having destinations per city, per town. That's his first example, okay? The net ID is the city, portion of your address. Then when you reach the city, then you will proceed forward to reach the final user, okay? But you will never find a very detailed information host-based in a router, okay? And in particular, how many of those, I'm coming to you, how many of those 32 bits are part of the network and how many of those are part of the host within that network depends on the mask. So you can select a subset of those bits and say, for example, okay, the first 24 identify the network and the remaining 8 identify the host within the network. And how many of those are the host depends on the mask length. The mask will tell me how many bits are used to identify the network and how many bits are used to identify the host. Yes? Okay, I repeat the question because otherwise, okay. The question is fairly complex. So the question is that suppose that you have a fragmentation process and those fragments go in a loop and only one of them actually goes in the loop, which is really almost impossible because typically all of them have the same destination address, they reach the router one after the other one, and so very typically either none of them goes in the loop or a portion of them goes in the loop if there is a mistake in the middle of this, so, but doesn't matter. And time to live expire, you will signal that to the source, and what does the source do? Nothing, okay? In the sense that the IP protocol does not ensure reliability. So that's just a signaling information that you get to the host, but in the IP layer, there is no automatic mechanism that you put in place under the fact that you receive an error message, okay? So you typically don't react. Maybe you react at higher layer protocol. It's just a configuration problem information. It's not related to the fact that you want to preserve the user data flow. It's a management function. So it's a network control function that you adopt when you drop a packet. So the IP protocol typically is doing nothing in that case, okay?
So basically, the ICMP packet that the source receives from that error is basically unused. I mean, because
well, it depends. You may
layer, for example, TCP, generally waits for the timeout expiration.
Okay, the normal behavior is that you have if you have on top of IP, you have TCP. TCP will see a packet drop. Okay, and from this perspective, the fact that after the packet drop you have sent an error message to the source has no implication on the data path. But you can act on a different type of layer and collecting these ICMP packets, and you can act at the management level in your network to do something, because if you have an error message, maybe there is a link that went down, so you want to run a protection scheme or something like that, okay? So it does not have an implication on the user data flow, but it may have other implications, okay? It may have other. But you may envision using this type of messages if you, for example, are using an application layer and you can ask through UDP to get aware of this INC packet, you can interact with the ICMP protocol and you can do something. I mean, it's potentially possible. Okay? Normally today it's not happening, but it's potentially possible. But the goal is different. The goal is to make aware the network manager that there is an issue in the network. It's not to help the user, because from the user perspective, we are unreliable. There is no guarantee. So if we drop a packet, we drop a packet. Okay? Let's forget about this. Okay, the last thing I want to tell about layer 3 is okay, is about some routing feature, which is not really strictly existing only in IP, is a general concept, and indeed, when we will talk about QoS algorithms, we will talk about QoS routing, and we will see again the concept of hierarchical routing in that case. Okay? So what does hierarchical routing means and why it is important? It is important to make the network scale. Why we are talking about hierarchical routing here when we revise IP? Because we are at a layer 3, and the main function of layer 3 is routing, selecting the best path. That's the main function of layer 3, further together with addressing. So you may say, okay, routing is conceptually is very simple. Every router is identical. Every router is a square. When you reach a router, you must find a destination address for any possible destination in the world, and that will work, but it's not practical. Okay, so we have a flat network. We have no hierarchy. All of the routers know any destination. That's simply not possible. We have scalability issues in terms of number of destinations. We have tens of millions of destinations. They cannot fit in a single routing table. Yes, you may try to simplify the problem. As we have said, we have several techniques. We have the technique of looking at networks and not a host, but still, it's very, very large. Furthermore, the routing information that you need to exchange to select the best path, we have not seen details about that. Okay, there are several techniques to do that, but conceptually, you have to exchange control information to make the router aware of the topology in some way, and on the basis of the knowledge of the topology, then you can run an algorithm to select the shortest path or the best path or whatever path you like on this topology. Okay, and now, of course, you have to exchange information about reachability of the destination because you want to reach the user. So you need to know where the users are connected to. So that routing information scales as a first approximation linearly with the number of destinations. And it's barely not possible to exchange it without simplifying that. So we need to have systems which scale better from these two perspectives. The last part is that the single flat network is not going to work even if we have ways of solving the previous scalability issues for administrative reasons. Okay? There is no single administrative domain in the internet. There are several providers managing their own portion of the network. And that has been since the beginning of the internet like that. There are several different portions and different administrator authorities are managing them with different criteria. Of course, we need to have exchange of information. We need to have some standards to do that. But within my domain, I want to be free to run and manage my network in the best possible way according to my criteria. Okay? And that's my autonomous choice. I don't want to have a general way of doing that. So for this reason, there is not the concept of running a routing algorithm on a single network, but there is the concept of running algorithms within a given domain, which is a sub-portion of the internet. So let's take first the idea of routing aggregation. Now, to make it simpler, let me give you this example. Think about, let's forget about IP addresses, which are a little bit strange, and I mean this concept of mask. But let's take the example of phone number, okay, which is a little bit easier to understand. But IP addresses works more or less in the same way. So if you look at the phone number, you know that there is an initial part of the phone number, which is the country code. Okay? And then, it's not true for mobile phones, but at least in some phone organization, if you look at plain fixed phones, a given number of additional bits identify a given area, geographical area. Okay? For example, in Torino, we have all of the numbers starting with 11. In Milan, all of them start with 2, in Rome with 6, and so on and so forth, after the country code. So we have first digits for the country code, then some digits for the area, and so on and so forth. And the idea is very simple, like it's very obvious. You are driving here in Torino, right? And would you expect to see a sign on which is the best road to reach Minneapolis in Torino? Not really, right? Who cares? Maybe you may be interested in finding a route that tells you, okay, if you want to go to the US, go to the highway. That may be useful, right? But you don't care about the details about Minneapolis or any other city in Dakota, or who cares, right? Even you may even not care about the difference between North and South America, right? Because at the end you have to cross the ocean somewhere, right? And typically to get out of Torino there will be one road that gives you reachability about London or whatever, where this huge bridge which connects UK with the US, okay? So that makes a lot of sense. So that's what we are trying to do. The first step in hierarchy in routing is address aggregation. So when you export out of your domain your addresses, which you assign, which you manage locally, you typically try to export them in an aggregated way. So that when you get out of Italy, you don't need to send and to communicate to all of the other European providers of the telephone network the specific details about each address in Italy. You don't care. You tell them, okay, everything which is starting with 39, send it here, send it to me. Then I will care locally about everything else to route properly within Italy. But if you are in Sweden and everything which is a phone call to Italy, send it here. So all of the 39 addresses I will declare with a single entry, with a single information, which is 39 addresses, phone numbers starting with 39, send them to me. And then I will take care about the other details. Once I get this phone number coming from Sweden, because this is a request to connect to an Italian phone number, then I will start looking in Italy at the next digit. And if it has to go to Torino, I will go on this road. If this has to go to Bari, I will go on this other road. But if you are in Sweden, you don't care. Everything is for Italy. Okay? So that's the hierarchical aggregation of addresses. You don't export any single address when you communicate with another administrative domain. Is it clear? Now, of course, this is country-based, but you can do that on a regional base, right? You are managing the network in Piemonte, and you know that everything that has the first digit after 39, which is 11, has to be sent it here, right? You don't need to give the details about any phone number in Torino. Who cares? Any phone number starting with 11, send it here, right? And then I will manage locally my sub-network. I will look at more digits to be more specific in terms of address to reach the user, okay? So that's very natural in routing process, okay? When you are driving your car, you start dealing about the details about the final roads in the city you want to reach only when you are there, right? But while you are traveling from Torino to Naples, who cares whether you want to go to Piazza Plebiscito or to another road? Doesn't matter. You have to reach Napoli first, right? And that's the routing information you use for a huge amount of time until you reach Naples. Then you will start looking with more details. So there is no point in writing very detailed information on the highway. Just put a big sign for Naples and that's it. Okay? And that's exactly what we do in the telephone network, and the same is done in the IP networks. IP addresses have the same logical, okay? The more bits you look at, the more detailed information you will have about routes. Okay? More specific. The less bits you use, the shorter the number of bits you use for the routing, the more you aggregate, right? If you declare an IP address whose length is 6, 2 to the, the packet length, the header, sorry, the address is 4 bytes, which is 32 bits. If you use 6 of them and you declare any address, 32 minus 6 is 26. You have 2 to the 26 addresses, users, cars, declared with a single entry, because you will not be able to distinguish them if you look only at the first 6 bits. Is it clear? If I tell you any number which starting with these 6 bits, send it to me, it means that 2 to the 32 minus 6 different addresses you will not be able to distinguish, because regardless of the values of those bits, all of them should be sent to me. So you see it here. I have several organizations within my domain, and I distinguish them according to the first 23 bits in the IP address. Okay? So everything which is different in the first 23 bits, I will have a different routing internally. Okay? So if your address is 233.16, you will go here. If your address is 223.18, you will go here, and so on and so forth. Clear? But when you declare this to the public internet, you will say, okay, everything which is 223.16, which is shorter, is only looking at the first 20 bits, send it to me. You don't care about the details. You don't have to look at more detailed and more specific information. Send it everything to my ISP, and I will locally manage looking at more bits to determine whether the final destination one is organization 0, 1, 2, 3, or 4, or 7. You don't care about these details. Is it clear? You declare shorter addresses. If you declare shorter addresses, you put in a single entry in your routing table many, many addresses. The shorter this length, the more addresses you compact in one entry. It's only one sign for a full country, for a full continent, for a full whatever. That's the idea. And that makes the system scalable. That reduces the number of entries in the routing tables. Okay? So any router will have some detailed information about local addresses and some more aggregate information about further addresses. Exactly what's happening here. You drive in Torino, you will find several signs for town around Torino, like you will find a sign for Asti, Alessandria, or whatever, but you will never find a sign for Catanzaro, for example. Right? You will find a sign that will tell you, okay, if you have to go out of Torino, take this road. That's the highway, and get out. Okay? Yes?
So basically, the routers that are, the gateway routers that are at the border of a given administrative domain of a given autonomous system basically have more information on the first bits in the address, while that is operate more on the first bit of the address, while the core routers of that system basically work much more on the part that is the more internal part, I mean, of the address.
Okay.
Much more specific information about that autonomous system rather than of how rich the address.
Okay, I cannot repeat the question because it will take 2 hours, but yeah, the basic idea, the basic question is, there are different types of routers, yes, and some of them at the periphery will have a lot of entries in the routing table which are significantly long because you have detailed local information, correct, but at the same time you may have also some shorter information for farther away destinations. So actually you have both of them. Maybe you may have more of the second type, of the first type, which is longer one with respect to the other one. There may be some other routers instead, which are the one more in the heart of the internet, which may have many entries, because you may have entries for maybe even more countries, like let's take the example of countries, but of shorter length. So you aggregate more, and this is in general true, yes. Now, stating if you have more entries in core routers, it really depends. It depends a lot, because it's true that at the periphery you have more detailed information, so you have more local addresses, but it's also true that you aggregate much more the other addresses in the world, right? Whereas in the core part, you have for sure you don't have many local information, true, but you may have more detailed information about what you want because you want to distribute in a different way. So it's not really true that the number of routes is larger here or there. That depends. That depends. And actually, core routers normally have fairly large routing tables. Okay. Also because locally, very often, you rely on the default route. The default route means if you don't find the detailed information about this address, do this. And clearly default routes are very much used at the periphery. Because in the periphery you have a local routing information, and everything else, well, get out of here. Get out of this ISP. And that's a huge way of compacting. So you have a single default route that tells you, okay, if you don't find the local address, send it out. And at that point, you compact a lot. Whereas you cannot have default routes on the core part of the internet, of course. So that depends. But for sure, shorter prefixes are more popular in the core part. Longer prefixes are more popular in the other part. Okay? Any other question? This is the detail. Okay, so to be a little bit more precise, what's happening in a end-to-end? So I think that the basic idea is clear right now. So you manage a local domain, you manage a portion of the network. Suppose that you are ISP capital B. You manage this portion of your network. In this portion of your network, you have a lot of local information. You may run your routing protocol. Nobody cares. You can do whatever you want as long as you reach the destination. It's up to you. Okay. Of course, there are standard protocols that are typically used, but if you want to devise your own protocol, nobody will care. And the same happens in domain A and in domain C, independently. Now we have a problem of exchanging information among domains. And this goes through the aggregation process, and you create a logical infrastructure of domain interconnections. So you have one router here. Let's take the example of this domain B. You have one router, which is router A, that you see is connected to routers belonging to other domains. You see? That's the only one in this example. Only one router in domain B is connected to routers belonging to other domains. These are called border routers. They are at the border of your domain. Okay? It's like border among countries, exactly the same, right? There are some roads, some points in which you have access to other countries. And typically this is a limited access point. So in this example, this router A is connecting through two other domains, and this means that you represent this domain in this domain, logical domain interconnection for routing purposes, okay? And this is true for any domain. Domain C has this router representing it. Domain A has two routers representing it in this interconnection logical topology, because you have two routers which are connected to routers in different domains, okay? So now what you do is that you run your local algorithm, you know your reachability, you know your best path, and you know your addresses. Then you have to export addresses, and while you do that, this node here will send to domain A and to domain C a reduced, compact information about local addresses by aggregating the addresses, shorter prefixes, okay? And you exchange this information through other type of protocols which are called inter-autonomous system routing protocols. You could use the same type of protocols. Typically you don't do that because you use simpler one, but they are independent. They are running independently. They allow exchange of information among domains. So router C will receive this information, which is aggregated, and will propagate it locally, because any router in that domain must know how to reach destination in domain B. Every router in domain A must be able to do that. So you get the information in router C here, and you propagate locally, so that any router knows how to reach destinations in domain capital B, with no specific information about local addresses. So the routing table of those border nodes is partly composed by local information, and typically with longer prefixes, with more detailed information, okay? And partly through the information that you get from other other domains. And you put them together to build the routing tables. So that you will find a lot of details about local addresses and some aggregating information about remote addresses. And what is going to be written here is that this router will tell the other routers, for all of these addresses, which are represented by a short prefix, so one single entry in my routing table, send it to me. Send it to router C. So if you want to go to Austria, you have to go to Brennero. Okay? Everything else doesn't matter, regardless of where you want to go in Austria. If you want to cross the border from Italy to Austria, you have to go there. So send it to me. Come here. Okay? And you propagate this within your network. So we'll typically have two types of protocols running. The local one, which are running in any router, and the border one, which are typically running only on border routers. Routers which are at the border of two administrative domains. And on these border routers, the routing information that goes through is aggregated, compacted, shorter prefixes. You declare less bits. Okay? Do you have any question about that? Is it clear? Okay, if it's clear, I think it's time, more than time, to have a break.